Okay. Y'all ready to learn about some Quines? Welcome to Evil Dojo. My name is Dark Mage. I've been on and off in computer science lecturing, tutoring, freelancing, among other things for the last, I don't know, 20 years or something like that. Um, Real talk, yeah, I was helping out fellow classmates when I was a senior in high school because my teacher ran out of things for me to do. I was 2 weeks ahead of everyone else on all of my homework assignments, captain of the UIL Computer Science League, and my teacher was like, just go around the class and see if anyone needs help. So here I am. I have made a career out of this somehow. While I have worked in industry, actually in corporate positions, the majority of my time has been spent freelancing, and a lot of that has been spent tutoring students in high school, college, as well as consulting with various people in positions of employment where they might be managing computers and have some need to learn how to write code. That's what I'm here for. And I'm kind of bored, honestly. Like, I'm on top of a lot of things, and I'm finding myself with enough free energy to actually learn a new programming language, right? So, I dabbled around a little bit with Go, and it's alright, but the real interesting thing is I'm no longer averse to working in Rust. And while I haven't done anything like crazy big in this language yet, I have started playing around with Quines. So we're going to talk about that. We're going to take a look and see what I've built so far. We're going to edit my existing code to add various features to the Quine generation process, as well as possibly do some Rust SDL later on if we got some time. I don't know how long I'm going to be on, but I want to kind of like freestyle it, just kind of see what happens, because I'm feeling confident enough to at least talk about it now. Like, I never want to talk about anything or even try to say shit that I haven't fully wrapped my brain around, right? And I've wrapped my brain around this enough that I should be able to just like freeball it, you know what I'm saying? So, not without a little assistance, of course, right? I need to let everyone know that we're live real quick. Let's see. Okay. Let me pull up chat on my phone so I can actually see you fuckers. Greetings, one viewer. There we go. What's happening, dope? How you doing, man? Alright. Let's get the show on the road here. Boom. Okay. What's a quine? So, let's talk about that. A quine is a computer program which takes no input and produces a copy of its own source code as its only input. The standard terms for these programs in the computability theory and computer science literature are self-replicating programs, self-reproducing programs, and self-copying programs. Quine is a fixed point of an execution environment. When that environment is viewed as a function transforming programs into their outputs, quines are possible in any Turing-complete language as a direct consequence of Quines' recursion theorem. For amusement, programmers sometimes attempt to develop the shortest possible quine in any programming language. Quines' recursion theorem. In computability theory, Quines' recursion theorems are a pair of fundamental results about the application of computable functions to their own descriptions. The theorems were first proven by Stephen Quine in 1938 and appear in his 1952 book, Introduction to Metamathematics. A related theorem which constructs fixed points of a computable function is known as Rogers' theorem and is due to Hartley Rogers Jr. The recursion theorems can be applied to construct fixed points of certain operations on computable functions to generate quines and to construct functions defined via recursive definitions. So that's an important point here, right? Recursive definitions. So the entire way that like a quine works is that you have a copy of the source code in the source code itself. Now that might sound weird, but hang on. The way that you get around this, or you kind of cheat, is by using a specific symbol that you predefine that generally wouldn't have any other meaning in the syntax of the language itself outside of a certain context. In this case, the most frequently used symbol for this process is going to be the @ symbol, and I'm going to show you what that looks like. We're going to take a look at the quine that I wrote in Rust. We're going to show how I got there. We're going to show how to extend it, and then we're going to start dabbling with, advanced shapes and art and stuff like that. See what all that we're capable of doing, and see how hard we have to work to actually do it. So a lot of this is motivated because of my interest in the works of Yusuke Endo, in particular his book, which I really, really, really want a physical copy of this book because it's fucking amazing. The World of Obfuscated Esoteric Artistic Programming. This is a book written in Japanese by Yusuke Endo, who has a GitHub at github.com/mame. So Yusuke Endo is also a winner of the International Obfuscated C Coding Contest, which I've been talking about trying to enter for a long time, but honestly, I need an idea and I need to practice before I even consider doing that. I admire the level of technical engineering required in order to make things like that and in order to make the things that Yusuke's made. This is why we're dabbling around with Rust and Quines. So I recommend you dig into his code and his work because it's absolutely fascinating and beautiful. He does a lot of work in Ruby, but he's skilled enough programmer to write quines in virtually any language. And literally, he's got a quine relay, which is an Ouroboros quine that generates each of 128 different programming languages, starting from Ruby and then going all the way around all the way back to Ruby again, rotating through all these different languages along the way. It must have taken a long time to put that together, for sure, right? He probably started small and then just like added each additional language. But he, certainly had a process for doing this. And as I'm going to show, there is a process for writing Quines in general. Where to start? Here we go. Okay. So the two tower Quine that I've written generates this exact output. This is the same program that just ran, printed back out, but split into two towers. The code that generated this looks like this. So the magic symbol here is the @ symbol, because what you end up doing, or needing to do in general, right, is embed the actual string representing all of this code into the source code itself. Now, how is that possible? Well, this is why we use the @ symbol here, because I kind of cheat a little bit. I use this as a template. As you can see, the file name is template.rs. And what this allows us to do is use it when we're generating a intermediary for the Quine itself. So for instance, if I were to run my make Quine program, it wants me to pass it a file. Make Quine is going to do some basic processing and pump out a stripped down version of the Quine itself. So the magic of the Quine occurs right here. That @ symbol has been replaced with a gigantic integer array. Each integer represents a different character in the source code itself. The @ symbol that we originally had in there is still in there, just in an integer form, and we have a real value here now that can actually result in an actually compiled program. My make Quine program is Python, but what it does is just simply strip out all of the leading white space and just left aligns all of the source code, so that when this actually gets compiled, the real Quine gets generated, and from that point on, the real Quine will always get generated from every subsequent run. So let's demo this out, right? We're going to go and compile that program. As you can see, it compiles with no errors, and if we try to run it, it generates what appears to be source code. If we write this out to test2.rs, we can see that indeed we have the source code now in the file, and if we were to run rustc on test2.rs, it compiles with no problems. If we were to run that, we get what appears to be the output of the program again. We can test this by writing it out to another file and then doing a diff statement on test2.rs and test3.rs. As you can see, the diff between the two files is the same. So this is a genuine Quine. How did I do that? How did I actually make it output two towers though? That's a very specific formatting, and there's a reasonable pattern of space in between the two towers. The towers seem similar lengths, with exception of a couple rows. And how did I achieve this? Let's take a look. So we're going to step through this like I step through any other program, and I'm just going to kind of go through what each line does. In the very beginning, we define a function called handle spaces. It takes an integer parameter called num spaces, and for every one of those values, we're going to just print an actual space. That way we can specify exactly how many spaces we want to print out, and just avoid having to have this for loop all over our program, because it's used in multiple places, and there's a reason for that. So in our function main, we're going to let v equals the @ symbol, because the @ symbol gets replaced with an integer array representing the source code after we run make Quine on this program. We're going to declare a mutable variable I, set it to 0. We're going to declare a column length to 20, and we can actually change this to whatever value we want. We're going to set column number to 0. That's also immutable, so it's going to change later. And we're also going to declare is inside quotes to be false, and this is mutable too. So for every character in our assumed integer vector, right, is really what we're doing is stepping through every character in the source code that's copied into the source code itself, and handling each character differently depending on different states, different variables, because ultimately for the artistic goal, you might want to print out the program in different shapes or different arrangements. So the rules for different shapes are all going to be more or less complicated and specific to whatever shape it is that you're trying to build. But in general, for every character, for instance, I just check to see if it's a new line, and we just skip new lines, because you could actually have a whole one-line Rust program if you want to, and the most basic Quine is, in fact, a one-line program. The @ symbol, when we encounter it in our integer array, represents the source code for the program itself. Now you're thinking, does it ever stop? And this is another reason we have to use integers in this case. How do I say this? Well, let's step through this. When we encounter the @ symbol in our integer array, first thing that we do is we want to print out a leading bracket, because this represents the integer array representing the source code, right? So it has to be a starting bracket to be an array. And then for every character index in that, or sorry, for every index in the source code array, we're going to print out the integer value of that source code. This is a little hack, because I believe with it, print won't let you pass in non-string literals for the leading argument. So we have to do this. But the nice thing is it actually prints out the real int value for us. We check to see what that value was, and if it was greater than 100, we're going to increment our I by 3, because the I represents, for this program, which part of the tower that you're currently rendering. So because there's two towers, I use the same I variable so that each tower can be essentially more or less the same length, or pretty close to the same length, so that we have very even towers. But if we have a number greater than 100 in our array, and we just printed that out, then we want to increment that by 3. If it was between 99 and 10, we want to print out increment by 2. And if it was less than 10, we're just going to increment it by 1. Then we check to see if that index value is greater than the column length, or in other words, the length of the tower. And if it is, if the column length was, or if the column number is 0, we're going to go ahead and print out a number of spaces equal to 20 minus I minus the column length. So it's trying to calculate like a difference between how far over you've currently printed. Because if we're defining each tower length to be like, say, 20, right? And we're in the middle of printing out some sequence of characters, and it's not a terminal character where we can add arbitrary white space in. A good example of this would be double equal sign. You can't have a space in between two equals because that's syntactically incorrect. You'd end up breaking your program. So we have to do it that way, right? We print out the spaces that way, and then we increment our column number by 1, so that if we're printing on the first tower and then we just print out a bunch of spaces, we want to tell the program, okay, now we're printing on the second tower. So that's why we do that. If the column number was 1, then we're going to new line when we're done printing this row, and then reset the column number back to 0 so that we can continue printing from the next row of the first tower. We set I to 0 if we ever, for either tower, finish for that particular row. We're going to reset I, because I ends up being used, like I said earlier, between both towers during the rendering process. The J corresponds to, so we're in the middle of printing the int array. And if the J is less than the length of the vector minus 1, so in other words, if we're not on the last character, after we print whatever number we just printed, we want to print a comma, because that's how you construct an int array, right? It's like int followed by a comma, followed by an int, followed by a comma, and for the last int in the array, you don't want to print a comma, you just want to close it. So we hit the comma, we increment our I by 1, and then we do the same check that we did earlier to handle the printing of spaces, because it's possible that after printing the comma, you end up with I equal to column length. So you want to handle that situation too. Excuse me. So once we finish printing all of the different int values in the array, we print a closing bracket and a semicolon. And that completes the printing of the int array back into itself. So that was for the first if statement in that whole thing. Else if the character was the @ symbol. So we're handling individual characters, right? So for every other character, we go ahead and print that character out, right? We take the int value and then we convert it into a into a character using this statement, char from u32 dot unwrap, and the C is the current int value that we're working with. we print that character and then we increment I by 1. I suppose that, well, no, we can't do a check for spaces yet, right? Because we don't necessarily know if what we just printed out is or is not a terminal symbol. Terminal symbols in this list, for instance, 32 is a white space. And it's not always going to be the case that we're able to print out on white space, right? But if it's a open curly bracket, if it's a closed curly bracket, let's see, what is 59? I think 59 is semicolon? Let's see. Yeah. 59 is semicolon. Semicolon, open curly bracket, so we're handling semicolon, open curly bracket, close curly bracket, and space. There's other symbols in here that we'd be able to treat in the same fashion to extend this list. So as an example of and actually the order of checking these is kind of backwards. We'd say C equals 32, or C is 59, 123, or 125. So what are some other symbols that appear in our program that we'd be able to break on and, you know, include in the calculations for whether or not we've reached the end of the tower generation, right? I believe parentheses. I believe equal symbol. No. This equal symbol could appear more than once. But plus 43, so if we said parentheses, right? 40 and 41. Space, open close parentheses, semicolon, and curly brackets. So, in other words, we're checking to see if the current character that we just printed out is a terminal sequence that we're able to just pad with arbitrary white space. Because those are useful characters to identify so that you can do crazy shit with them. I believe we can actually have plus equals. With arbitrary spaces, but we'll test that. So, if our character is any one of those terminal symbols, and our I is greater than or equal to the column length, or in other words, the length of the tower, and if we're not inside of double quotes, because double quotes being a situation where we don't want to add arbitrary white space when we're printing it out. We want to preserve the formatting of any strings, any hard literal strings that we unfortunately have to have in the program for it to work, because that would result in our program breaking. So check to see if we're not inside the quotes. And if the column number is 0, and if, oh, we don't need 2 column number zeros. Did I just accidentally add that? Okay, if column number 0, then we print the spaces, which we define as 20 minus I minus column length, and then we increment our column number by 1, just like we did earlier when we were printing out the vector. We have to separate the logic between these two, because in one case, we're handling what happens when we reach the @ symbol, and in another case, we are handling every other character, kind of, as we receive them. Because a lot of the characters we can kind of treat the same like this, just as you can see here. Else we print a new line and we reset the column number to 0. I is equal to 0 again after that, so that we reset the printing of the tower. And that's what happens if we reach one of those terminal symbols. Else, if we reach a double quote, then we're going to turn the first time we receive a double quote, this is going to become true. The next time we receive a double quote, this will become false. And so that way we can separate out the handling of string literals when we're printing out the program. Close, 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 and that's the end of the Quine. So let's make sure that, of course, it's going to still work. So when you call make Quine, you pass in template.rs. This produces the intermediate representation. Now when we run test, we are actually factoring in parentheses now to our tower generation. So we're also factoring pluses and some other symbols, but the parentheses in particular. So to verify that this still works, we write it out to a new file, we rust it, and then we run it. And as you can see, they are the exact same program. So the next step here excuse me. So I actually have a one-liner here for generating Quines. So we can use this during our testing to make things a little bit faster. I recently added in the ability to allow for comments so that it doesn't break when it generates the intermediary. It just strips out anything containing double slash like this. Which, very useful, right? But naturally, you could generate Quines that contain comments. But that's not my focus. and I haven't actually sat down to play around with that idea yet. Yeah, you could technically break before parentheses, and that's actually the next step that I want to implement right now. Is what's required for that, right? Like what's actually required in order to do something like that would be the ability to do character look ahead and look behind. In order to do that, we're going to have to rewrite, or rather change the way that we're doing our loop here. This is going to be a question of, let's see, so for k and v dot length, let c equal v of k. So this would result in the same thing working. Let's verify that. Okay. So that was an easy enough change. Character look ahead and look behind, right? So we now have a dedicated loop variable k, allowing us to iterate through the contents of the vector. Without having to do it in a for each style way. So when we print a character, if we wanted to do look ahead, right? Like, if we print a character out and the next character is a open parentheses, if v of, so first of all, if k plus 1 is less than v dot length, so we get next character if next char is exactly equal to open parentheses, which is 40, we could actually handle the white space. And then increment column number plus 1. So I don't think there's going to be a situation where if we do the look ahead, see, I need to include these both as the same thing, right? So, and v of k plus 1 exactly equal to 40. Because if the second one's not true, so if, like, for instance, we do a look ahead and if we're able to do a look ahead and the character happens to be if it happens to be an open parenthesis, then we can print our spaces and increment the column number. So we only if column number is exactly equal to 0. Else, we print a new line and we reset column number. So that should be easy enough. Is there any other symbol that we would want to check for? Open curly bracket, right? So if we're able to do a look ahead and v of k plus 1 is open parentheses or v of k plus 1 exactly equal to 123, uh-oh, we got an error. Oh, we got a warning. It's yelling about the parentheses around the if, and it's also definitely breaking the rendering here. So if k plus 1 is less than length and v of k plus 1 is open parentheses, oh, but we're not checking to see if our I is greater than column length. We need to do that. So yeah, we only want to do all this if I is greater than or equal to column length. There we go. Okay. Now that's created something really interesting. Oh, we're not resetting the I. We need to do that. There we go. Ooh. Don't you just get all excited when your code works? Let's make sure this actually works. Oh, that did something different. No, it's the same. Oh, wait. Okay, no, they're actually the same. Hooey! God. Um, so we're actually implementing look ahead now. We check to see if the next character goes over our, well, no. Yeah, we check to see if our next character goes over a limit, and it happens to be a character that we're able to do white space on. There will be certain characters that we can get away with this doing. So, for instance, open curly or open parentheses would count. Now, a lot of the code that we're using to like handle the columns and stuff is really repetitive and found in a lot of different places. We could probably find a way to pull this out into a function because you know we want to be good programmers about this, right? Let's make sure this still works. Okay. Now, what if we were to just play with the size of the column? Now we got much thinner. Um, we're going to eventually have to be able to handle multiple character look ahead if we wanted to handle like being able to space out based off of keywords such as if and else, for, and so on and so forth. One of the goals too is to be able to do this randomly. And so whenever we're generating a new instance of the program, is there any way you can do a random number from 10 to 40? Uh-oh. think this is where we get into the problem of the way that I'm building this, right? Oh. Let's see. Use rand RNG. Oh, I have to put it in my Alright, so this actually writes out the test.rs, right? So you copy test.rs into source main. We update the cargo.2ml file. So we can put the rand dependency in there. It's got to grab a lot of stuff for fucking random. Oh, it says it's unused. Oh, well, technically, I'm not yelling about our result there, but there we go. Okay, so oh, that's interesting. Let's see, that's kind of a wide variance. Alright, so we're going to update generate Quine. So we can still edit and use template. There we go. Okay. Test2.rs. Now, yeah, it's going to yell about that, naturally. Alright, let's get, I mean, we can never really be sure which one we're going to get here. I want to try compiling one of the thin ones. There we go. Okay, let's cargo build. Oh, we got a Okay, so we cannot do spaces on plus like that. Right, because we need to do the look ahead just for that one. So plus symbol is 43. Nice. Okay, so that's a thin one. Let's cargo build that. Oh, fuck. Oh no, that's terrible. Oh shit. Shit got real fucked up there. Uh, we're going to comment out the look ahead for right now. Make sure that, or just verify that the randomness aspect works. Oh shit. Okay, we got a thin one there. Let's cargo build that. Okay. Oh. Alright, let's compile that. Because as you can see, we got two towers. One of them just commas, the other just numbers. This is a valid Rust program. And it still generates a random sized set of towers. And every single one of them is a valid Quine. It prints out its own source code. It may not be the exact same as the previous one, but this is an example of how you can introduce randomness into the Quine generation process in order to start to vary your output in such a way that the program is still valid, that you compile, but it's a different result or different formatting than the previous one. The idea here being that the next step past this would be generating images in sequence, generating iterative things that grow with each subsequent compile. Um, there's a lot that you can actually do with this kind of setup here. Okay, that one's good. We're going to add an example output to our README, just so people can see right away without having to run anything. Okay. Progress. Okay, so this is the current state of the working folder. Um, it's relatively clean. Not sure how much more we can do here. I know I said I might do some Rust SDL stuff, but I'm honestly not feeling it. Might just take a break and dick around. This is very similar to some of the C stuff I've done for in Quine, or some of the C Quine stuff I've done, I should say. Some of those I got up to N tower generation, so it would not only randomly size each tower, but it would also generate a random number of towers. Some of the future shape targets could include just generic boxes or squares, which, now that I've implemented the look ahead, we would be able to start calculating how many characters we're able to fit on a particular line, and then adjust the line itself based off of, like, for instance, we could add arbitrary spaces in between certain characters in order to make it more properly spaced out on a particular line, for instance. A lot of that stuff is pretty intensive. Not to mention, if we wanted to do anything more advanced, involving character compression, more complicated shapes like Japanese character symbols, so on and so forth. I shouldn't push myself too hard. This has been a pretty active stream. I did a lot for the hour that I've been here. I want to thank y'all for joining. Thank you for watching. If you're not down with Evil Dojo, you should be and you will be, because you're going to hit that like and subscribe. You're going to hit that Twitch Prime. You're going to do all of that good support nonsense that anyone hanging around long enough to listen to this stuff, watch and learn. We're doing some crazy stuff here, and we're doing it in new languages, so we're keeping the education train rolling. Thanks again, everyone. Take it easy until next time.